Let's begin our journey on the ship of the imagination. Our first stop is the star at the center of it all, the Sun. It holds 99.8% of all the mass in our solar system. This immense gravity is the anchor for everything that follows. We venture outward, first to Mercury, a scorched little world racing around the Sun in just 88 days. It's so close that the Sun's pull is incredibly strong. Next we visit Venus, a toxic greenhouse shrouded in thick, acidic clouds. Curiously, it spins backward, a cosmic rebel with a day longer than its year. This is a place where the Sun rises in the west and sets in the east, a testament to a violent past. We continue our voyage to our home, Earth, the pale blue dot. It's a perfect distance from the Sun, in what we call the habitable zone, where liquid water can exist. This is where life, as we know it, took hold. Beyond our world lies Mars, the red planet, with its rusty dust and polar ice caps. It carries the scars of ancient rivers and lakes, whispering tales of a once wetter past. Think of these first 4 planets as the inner rocky worlds. They are small, dense, and relatively close to each other. Their proximity to the Sun dictates their swift, tight orbits, a constant high-speed chase around our parent star. Now we cross the asteroid belt, a vast debris field of rock and ice, the remnants of a planet that never formed. This is the boundary between the inner and outer solar system. On the other side, we meet the giants. First is Jupiter, a colossal gas giant, larger than all the other planets combined. Its great red spot is a storm that has raged for centuries, big enough to swallow our entire Earth. Jupiter is like a mini solar system itself, with dozens of moons, each a world of its own. Its sheer size and gravity have a profound effect on the entire system, acting as a cosmic bodyguard that deflects comets and asteroids. Our final stops are the other gas and ice giants, Saturn, with its magnificent shimmering rings made of countless ice particles. The rings are a spectacle of light and shadow, a cosmic hula hoop of incredible scale. Then we reach Uranus and Neptune, the distant deep blue ice giants. These worlds are cold and mysterious, so far from the Sun that their years last for many Earth decades. Neptune, the last official planet, takes 165 Earth years to complete a single trip around the Sun. This grand tour reveals a beautiful, orderly system, all held together by an invisible force we are about to explore. So what is this invisible force that choreographs the cosmic ballet of the planets? It's gravity. Every object with mass pulls on every other object with mass. The more massive an object, the stronger its pull. The Sun, being the most massive object by far, exerts the most powerful gravitational pull in our solar system. It's like a cosmic anchor, holding all the planets, moons, asteroids, and comets in their place. This force reaches across vast distances of empty space, a silent, persistent tug that dictates the motion of everything from a tiny pebble to a giant planet. But if the Sun is constantly pulling the planets toward it, why don't they just fall in and burn up? The answer lies in their motion. The planets are not just sitting still, they are moving sideways at incredibly high speeds. Imagine you throw a ball. It moves forward, but gravity pulls it down, so it follows a curved path to the ground. Now, imagine you could throw that ball so fast that as it falls, the Earth curves away beneath it at the same rate. The ball would never hit the ground, it would be in orbit. This is exactly what the planets are doing. This perfect balance between the forward motion of a planet, its inertia, and the inward pull of the Sun's gravity is what creates an orbit. The planet is always falling toward the Sun, but it's also moving sideways so fast that it constantly misses. This continuous falling and missing dance is what we call an orbit. It's a stable, repeating path that the planet can follow for billions of years. This is the fundamental principle that governs not just planets around stars, but moons around planets, and even our artificial satellites around Earth. The universe is full of these elegant, balanced motions. We measure the vast distances in our solar system using a special unit called the astronomical unit, or AU. 1 AU is the average distance from the Earth to the Sun, about 150 million kilometers. Mercury is less than half an AU from the Sun, while Neptune is about 30 AUs away. The time it takes for a planet to complete one full orbit is its orbital period. For Earth, that's 1 year. For distant Neptune, it's 165 Earth years. The farther a planet is from the Sun, the weaker the Sun's gravitational pull, and the slower the planet needs to move to maintain its orbit, resulting in a much longer year. For centuries, we looked up at the sky and wondered about the paths of the planets. They didn't seem to move in perfect circles. It was the astronomer Johannes Kepler who finally cracked the code in the early 1600s. He discovered 3 fundamental laws of planetary motion. His first law was revolutionary. Planets move in ellipses, not perfect circles, with the Sun at one of the 2 foci of the ellipse. This means a planet's distance from the Sun changes throughout its orbit. Sometimes it's closer, and sometimes it's farther away. This simple discovery changed our understanding of the cosmos forever. Kepler's second law describes how a planet's speed changes during its orbit. He found that a planet sweeps out equal areas in equal times. In simpler terms, this means that when a planet is closer to the Sun in its elliptical path, at a point called perihelion, it moves faster. When it is farther away, at aphelion, it moves slower. Think of an ice skater pulling their arms in to spin faster. The planet does the same thing as it gets closer to the Sun, speeding up in response to the stronger gravitational pull, and then slows down as it moves away again. It was Sir Isaac Newton who later explained why Kepler's laws worked. He formulated the law of universal gravitation, which described gravity as a force dependent on mass and distance. Newton's physics gave us the mathematical tools to predict the motion of celestial bodies with incredible accuracy. He showed that the same force that makes an apple fall from a tree is the one that keeps the moon in orbit around the Earth and the Earth in orbit around the Sun. It was a unifying moment in science, connecting the heavens and the Earth under a single set of physical laws. But the story doesn't end with Newton. In the 20th century, Albert Einstein gave us an even deeper understanding with his theory of general relativity. He proposed that gravity is not a force, but a curvature of spacetime itself. Massive objects like the Sun warp the fabric of spacetime around them, like a heavy bowling ball placed on a trampoline. Planets are simply following the straightest possible path through this curved spacetime. This new perspective explains subtle details that Newton's laws couldn't, like the tiny slow precession of Mercury's orbit around the Sun. Einstein's theory of relativity has very practical applications right here on Earth. The Global Positioning System, or GPS, that many of us use every day would not work without it. The satellites that make up the GPS network are orbiting Earth at high speeds and are farther away from Earth's gravitational pull than we are. According to relativity, this means their internal clocks tick slightly faster than clocks on the ground. If engineers didn't account for these relativistic effects, the GPS system would accumulate errors of several kilometers every single day, making it completely useless. Your phone knows Einstein's physics. Our solar system is also filled with beautiful examples of orbital harmony. Look at Jupiter's 4 largest moons, discovered by Galileo. The inner 3, Io, Europa, and Ganymede, are locked in a perfect orbital resonance. For every one orbit Ganymede makes, Europa makes exactly 2, and Io makes exactly 4. This precise clockwork-like relationship keeps their orbits stable over eons, a gravitational synchrony that creates a rhythmic celestial dance. It's a reminder that the laws of physics can produce not just order, but a kind of cosmic music, a harmony of the spheres that Pythagoras dreamed of. And the dance doesn't stop at the edge of our solar system. Our Sun, along with its entire family of planets, is also in orbit. We are all moving together on a grand journey around the center of our home galaxy, the Milky Way. It takes our solar system about 230 million years to complete one trip around the galactic center. We are all passengers on this giant cosmic carousel, part of a swirling city of hundreds of billions of stars. The same laws of gravity that hold the planets in orbit around the Sun also hold the Sun in its vast orbit around the galaxy's core. When we look up at the night sky, we are not just seeing points of light. We are witnessing the grand, unfolding story of the cosmos. We see the result of billions of years of gravitational interactions, of orbits shaped by invisible forces and the very fabric of space-time. It's a complex, intricate ballet, playing out on an unimaginable scale. And to know that we are a part of it, to understand our place in this cosmic dance, is a profound and humbling experience. It connects us to the universe and inspires a sense of wonder that is at the very heart of science.